Are you able to see my screen?
Yes, sir.
Yeah. So very good afternoon. Today we rescheduled our lecture to 12:15 due to an ISO audit. On Monday's lecture, we had started with our sixth unit, that is graph. We have discussed that graph is one of the non-linear data structure in which the elements are organized in the random fashion. Here the elements are represented with help of node or vertex, and these nodes or vertex are connected to each other with help of edges. So mathematically we define graph as v comma e, where v is set of vertices and e is set of edges. So this is one example which we had seen on that day for one particular. With that, we have also discussed about the basic terminologies related to graph, like adjacent vertices. We say that two vertices are adjacent to each other if there is a connecting edge between those two vertices. Then we have seen definition of path. Path is basically the collection of edges in consecutive fashion. Then we have cycle. Cycle is basically a path in which the first and last vertex is same. Then we have also discussed about connected graph and unconnected graph. So sometimes we can have some part of our graph not reachable from some other part. Here we can see that I'm not able to go to 4 and 5 from 1. I'm not able to go to 4 and 5 from 3 and from 2 also. Likewise, I'm also not able to come to 1 from 4 and 5, right? So there is a disconnection between this, but this entire thing is treated as a single graph because mathematically we said that graph is v comma e. So I can have a graph like v1 comma 2 comma 3 comma 4 comma 5 and edges as e1 comma e2 comma e3 comma e4, wherein now this graph would be treated as an unconnected graph, right? Then we have seen degree of graph. Okay, then we have seen degree of graph. Before degree we have seen directed graph also, right? So if your edges are having directions, then such type of graph is termed as a directed graph. If your graph is undirected graph, then the same edge can be used to go from both the vertices to each other, right? So in an undirected graph, if I have an edge like here, if I have an edge e1, this is from 2 also and from 1 2 is different and edge 2 1 is different, right? Likewise here we have edge 2 5, but there is absence of edge 5 2. So I cannot come from 5 to 2 because I don't have an edge here from 5 to 2. Then I may look out for some path or so, if at all it exists, right? So in case of directed graph, we have directed edges, and each of these edges will have a source and destination vertex, right? So for this particular edge which I pointed out right now, the source is 2 and the destination is 5. So this is 2 comma 5. 5 comma 2 will be a different edge altogether. Now in directed graph, we will be having directed paths. So this is one example which I quoted on that day. 1 comma 3, then followed by 3 comma 4, then followed by 4 comma 5. So this is the directed path from 1 to 5. Similarly, the cycle will also be a directed cycle. Cycle will also be a directed cycle in which it will be a directed path where the first and last vertices are same. So directed cycle is a cycle, is basically a directed path in which the first and last vertex are same. Then we have seen definition of degree. Degree for the undirected graph is directly the number of associated edges for that particular vertex, right? But when it comes to a directed graph, the degree is divided into two components, in degree and out degree. In degree is number of incoming edges and out degree is number of outgoing edges for that particular vertex. And the total degree is basically addition of in degree and out degree. Then we have seen two more definitions, that is complete graph or fully connected graph. Now we say that a graph is complete or fully connected if there is a edge from every vertex to every other vertex of that particular graph. So all the vertex are connected to each other with help of edges. For such type of graph, we call it as a complete graph. And finally, we discussed about weighted graph. So in weighted graph, for each of the edges, we will be having some weight value associated with it. So I had given you one example of we can have these weights in the form of distances between the two cities. So I had given you one example of Google Map that day, right? So your cities will be treated as your vertices, These edges are nothing but roads and the numeric values are nothing but the distance, right? So to formulate such type of problems, graph data structure can be used. And finally, we had seen the relationship between tree and graph. Now tree is basically a type of graph. So we can say graph is a superset, we can say, and tree is a subset of that graph. Graph can be treated as a set and tree is a small subset of that graph. So we can comment that all trees are graph, but all graphs are not tree. All trees are graph, but all graphs are not tree. And finally, we had seen definition of tree with respect to graph. A graph is said to be tree if it has two properties. What were those two properties? First one, it has to be connected. It has to be connected. And second, there are no cycles in that graph, because we know that in tree there are no cycles, right? So there should not be any cycles in that particular graph and it should be connected. Then only we can call that particular graph as a tree. Then only we can call that particular graph as a tree. With this, today we will start our, that is graph representation. To discuss that is graph representation. So all of you make note of it in your notebooks. Graph representation. Graph representation. We all know that for all the earlier types of data structures also, we had two representations, static and dynamic, right? Static usually we used to do in the form of array and dynamic usually in the form of linked list. So the same concept is there in the graph representation also, but here some names are given. For static, we call that representation as adjacency matrix. This is basically the static version, static representation of your graph. This is basically a static representation of your graph. The second one is adjacency list. The second one is adjacency list. The second one is adjacency list. It is dynamic one. It is dynamic one. So let us discuss these two graph representations today one by one. So first let us discuss adjacency matrix or the static representation of our graph, or the static representation of our graph. Now usually this representation, what it tries to do is it tries to maintain the information about the adjacent vertices. Okay, that's why the name given to these representations are having the word adjacency into it. What this representation tries to do is it tries to store the information related to adjacent vertices. What it tries to store? It tries to store information related to adjacent vertices. Which vertex is adjacent to which other vertex? Such type of information we are trying to store in the graph representation. And that's why both the representations are given label as adjacency. One is static with help of matrix and another is dynamic with help of list. So first I'll tell you what is that matrix representation. I'll take one example. Okay, I'll take one example. Okay, suppose this is your graph. This is vertex number 1, vertex number 2, vertex number 3, vertex number 4. Okay, and I'm constructing some edges over here. Suppose these are the edges which I have constructed. Okay, suppose this is my given graph. Suppose this is my given graph. I'll take one more. I'll take 5. Suppose this is my given graph. So the adjacency matrix for this graph will be of size n by n. What is the size of the matrix? Size of the matrix is n by n, where n is nothing but the number of vertices in my given graph. What is n? N is number of vertices in my given graph. How many vertices I do have in my graph here? I have 5 vertices in my graph. I have 5 vertices. So what will be my matrix size? It will be 5 by 5. What will be the size of my matrix? Adjacency matrix. Size of my adjacency matrix will be n by n. What is n here in our example? It is 5. So I will be having 5 by 5 matrix. So how that 5 by 5 matrix will look like? It will look like this. So I have my dimensions of rows and columns. I have my vertices on the dimension of rows and columns. I have 5 vertices, right? So 1, 2, 3, 4, 5. So all these 5 vertices you can see are there in my dimensions. They are there in my dimensions. Okay. Now, what this matrix will have? Now this matrix, if I call this matrix is a matrix A, suppose this is an A. Okay. Now any value in this matrix, that is Aij will be either 1 or 0. I'll be having values here in the form of 1 and 0. When I'll be having value as 1, if there is an edge, between vertex Vi and Vj, then only Aij will hold 1. What it indicates? 1 1. Now 1 1, do I have any edge of 1 1 over here? No. What could be 1 1 edge? Like this. This can be treated as 1 1 edge. So I'll draw this. Okay, I'll draw one of them so that it will be easy for you to understand. So whether I have a 1 1 edge over here? Yes, 1 1 edge is present. That's why I'll be writing 1 over here, because there is an edge. And if there is no edge, then it will be 0. Then next, whether there is an edge between 1 and 2? Whether there is an edge between 1 and 2? Yes? Can anyone tell me whether there is an edge between 1 and 2?
No, sir.
No.
No.
So this will be 0 then. Whether there is an edge between 1 and 3? Yes. So this will be 1. Whether there is an edge between 1 and 4? Yes. So this will be 1. Whether there is edge between 1 and 5? No. So this will be 0. We are talking about edge, student. Remember, it is about edge and not path. There may be a path, but there is no direct edge. There is a difference between edge and path. So when it comes to adjacency matrix, we are representing adjacent vertices, and the definition of adjacent vertices is based on a direct edge and not on the basis of path. Okay. Next, 2 1 will be again 0. 2 2 we don't have, so it will be 0. 2 3, yes, there is an edge. 2 4 there is an edge. 2 5 there is an edge. 3 1 there is an edge. 3 2 there is an edge. 3 3 there is no edge. 3 4 there is an edge. 3 5 there is no edge. 4 1 there is an edge. 4 2 there is an edge. 4 3 there is an edge. 4 4 there is no edge. 4 5 there is an edge. And for 5 1 there is no edge. 5 2 there is the edge. 5 3 there is no edge. 5 4 there is edge, and 5 5 there is no edge. So is this example of adjacency matrix for this particular graph understood? Yes. Is it clear?
Yes, sir.
Yes. Now, my dear students, this is for an undirected graph. This is for an undirected graph. Okay. Suppose you have a directed graph. Say for example, now you are having a directed graph. So I'll take one example for a directed graph now. So suppose I have vertices 1, 2, 3, 4, 5. This is my graph, and now my graph is directed graph. My graph now is a directed graph. So the edges in this graph are having directions. Okay, suppose this is the directed graph which I have taken. Is this figure visible to you properly? Directed graph?
Yes.
Yes, sir.
Yeah. Yeah, now again this will have a matrix of size n by n. So I have all my vertices 1, 2, 3, 4 and 5. All I have all the vertices here in the column definition also 1, 2, 3, 4, 5. Now these vertices over here are treated as source vertices, and these vertices over here in this dimension are treated as destination vertices. Why I need this distinguishing factor? Because we all know that in a directed graph, edge 1, 2 is different and 2, 1 is different. If I see here, I didn't have any problem. 1, 2 and 2, 1 were same, right? So if 1, 2 was 0, then 2, 1 was also 0. I was getting a symmetry in my matrix. But that will not happen here in case of an undirected graph, because here 1, 2 is a different edge and 2, 1 is a different edge, right? Now whether I am having 1, 1 edge, yes, I am having 1, 1 edge, so I am putting 1 over here. Whether I am having 1, 2 edge, whether I am having 1, 2 edge, yes, can anyone tell me whether I am having 1, 2 edge?
No.
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 See my students,
No.
this edge which is there in my diagram is from 2 to 1. Carefully observe, this is from 2 to 1, right? This is not from 1 to 2. The value over taking this. So this will 1, 3 will be 1. 1, 4 is again 1. 1, 5 is 0. Did you get this? Yeah. Now 2, 1. Yes. Now 2, 1 will have value 1 because I have an edge from 2 to 1. 2, 2. I don't have any edge 2, 2. 2, 3. No, I don't have any edge. 2, 4. Yes, we do have an edge. 2, 5. Yes, we do have an edge. 3, 1. 3, 1. Do we have an edge? Yes. Can you tell me? 3, 1. No.
No. No.
Correct. 3, 2. Yes. 3, 3. No. 3, 4. No. 3, 5. No. 4, 1. No. 4, 2. No. 4, 3. 4, 3. No. 4, 4. No. 4, 5. Yes. 5, 1. No. 5, 2. Yes. 5, 3. Yes. 5, 4. Yes. 5, 5. No. So this is my adjacency matrix for the directed graph. Is it clear both the examples how we represent adjacency matrix for a directed graph and for an undirected graph? Are both the examples clear? Anyone is having any query, any doubt? Yes. Am I audible, students?
Yes, sir.
Yes.
Yeah.
Yes, sir.
Is it clear how we represent adjacency matrix for directed graph
Yes,
and
sir.
undirected? Yes.
Yes, sir.
So now students, imagine that I'm having a graph like this. Suppose I'm taking another figure now. Suppose I'm having a graph like this. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and I'm having these edges. Okay, suppose this is my given graph. Suppose this is my given graph. Now, my dear students, tell me what will be the size of my matrix?
Eight by eight.
8 by
8 by 8. Very good. The size of my matrix will be 8 by 8. So total 64 cells will be there for me to store. And actually, how this is an undirected graph, right? This is an undirected graph. How many edges I do have here over here? If I count, I have 1, 2, 3, 4, 5, 6, 7, 8 edges are there. And being a undirected graph, it will be 8 multiplied by 2 means 16 entries. Because 2, 5, 5, 2 are same, right? 1, 2 and 2, 1 are same. 1, 8 and 8, 1 are same, right? So if I say that I have this 3 and 2, 5 and 2, 7 and 8. If I have 8 edges, I will have 16 entries. How many entries I will have? For 8 edges, I will be having 16 entries. And how much matrix I have? Actually 64. So I allocate 64 slots to store, but I'm actually utilizing meaningful data of only 16. And suppose if this graph is directed, suppose if this is a directed graph, then what will happen again? Suppose this is a directed graph, then again it will not be 16, then it will be only 8 edges. So out of 64 slots, I am properly utilizing only 8 because I wanted to store information about only 8 adjacencies, but I allocated 64 slots for it, right? So it doesn't become an effective representation. It doesn't become an effective representation. Did you understand the drawback of static implementation? So this is one sort of skewness also we can say. In trees, if you remember, I had taught you skewness, left skewed tree and right skewed tree. So that was the drawback. The skewness was the drawback of the static implementation of trees. Similarly, there can be skewness in graph also. What is skewness? If I have very less number of edges and more number of vertices. So if my number of vertices start increasing, then my matrix size will also increase because matrix size is n by n, where n is number of vertices. And if I have only less number of edges in that graph, then I am allocating more size, but I am representing only limited adjacency information in it. So adjacency matrix, that is static implementation, is not a fruitful solution in those cases. Then in that cases, we need to go with the second approach, that is adjacency list. In that case, we need to go with the second approach, that is adjacency list. Is the drawback understood of adjacency matrix? Is the drawback understood? Do we have Karthik? Karthik is there in this lecture. Karthik. Yes, Karthik.
Yes, sir.
Yes. What is the drawback of adjacency matrix? What did I explain just now? What is the drawback of adjacency matrix?
So if we have any the all the hello.
Hello.
Yes, sir.
Your voice is little breaking. Can you repeat the answer once again?
So the space is getting allocated, but all the spaces are not getting used.
Why it happens? Because there are less number of edges, right? Because there are less number of edges, right? So in such kind of skewed graph, okay, so in such kind of skewed graph, or we can say that these graphs are sparse graph also. Okay, we can also call these type of graphs as sparse graph because that will produce us sparse matrices. That will produce us sparse matrices. What are sparse matrices? Such matrices in which there are more number of zeros, where there are more number of zeros, right? So in such cases, we may have second type of implementation, that is adjacency list. We may have second type of implementation, that is adjacency list. So in adjacency list, we have total n lists. How many lists are there? N lists, where your n is nothing but again number of vertices. Where your n is nothing but number of vertices. So we'll take example. Suppose this is your given graph now. Okay, and I'm constructing now few edges only. Okay, suppose these are the edges of this graph now. Okay, these are the edges of my graph. I'll take one more over here. Okay, these are the edges of my graph, suppose. So how many vertices are there in this graph? 5 vertices are there. How many vertices are there? 5 vertices are. So I'll be having 5 linked lists. How many linked lists I'll be having? I'll be having 5 linked lists. So for this 5 linked list, I have 5 external reference pointers. So these are my 5 external reference pointers. Okay, this is for first vertex, this is for second vertex, this is for third vertex, this is for fourth vertex, and this is for fifth vertex. What are these? These are my 5 external reference pointers. Now what is linked list of 1 going to do? It is going to store adjacent vertices of the vertex 1. Which vertices are adjacent to 1? 2, 4 and 3. What are the adjacent vertices of 1? 2, 4 and 3. So this will be stored here. 2 in singly linked list form. 4 and 3. See my dear students, we are not interested in the sequence in which you are storing. I can store like 4 to 3 also, 4 3 2 also, 3 4 2 also, 3 2 4 also, 2 3 4 also, right? It is not important that in what sequence you are storing it here, but what is important is that all these 3 are adjacent to 1. What information this adjacency list tries to convey is that for 1, 2, 4 and 3 are adjacent. Don't apply a logic like this that 1 is adjacent to 2, 2 is adjacent to 4, 4 is adjacent to 3. No, don't go in that misunderstanding. What this linked list is indicating? This linked list is indicating the vertices of 1. Which are the adjacent vertices of 1, 2, 4 and 3. So I am storing this 2, 4, 3 here. One can store like this also, 3, 4 and 2. 3, 4 and 2. He can write like this also. Someone can write 4, 2, 3. So the sequence here inside is not important to us, but what is important is that these all should be adjacent to 1. There is no relation between 2, 4 and 3 here internally. What is the relation actually? That these all are adjacent to 1 is the only relation. It is the only information that is conveyed from this first linked list. Is it understood? Then now, what is the adjacent vertices of 2? Now in that, I'll be having linked list of 2. What are the adjacent vertices of 2? Adjacent vertices of 2 are 1 and 4, right? So I'm storing 1 and 4 in this linked list. Is it understood, my dear students? Which are the adjacent vertices of 3? Which are the adjacent vertices of 3? 1 and 4. 1 and 4. Which are the adjacent vertices of 4? 1, 2, 3 and 5. Right? 1. I'll draw one loop also here so that that entry will also be understood to you. 1, 2, 3 and 4. Which are the adjacent vertices of 5? 4 and 5. Very important. 4 and also 5. Is this understood?
Yes, sir.
Is the adjacency list representation understood here in this case?
Yes, sir.
Yeah. Now I have one question. Let's see who will answer this. Suppose for one graph, I have constructed this adjacency list. Like I have done it right now. This was the given graph and I constructed this list here in front of you, right? So suppose there is one more graph, for which a list is constructed and being presented. Suppose in that particular list, suppose you have one vertex like this, and suppose it is indicating like this. What is meaning of this? Can anyone tell me? What you will understand from this?
Sixth node is in graph, but it is not connected.
That node is not connected
Unconnected.
to any unconnected. What is the perfect word? I had taught you one.
Isolated. Isolated vertex.
Very good, very good. So this 6 in that case would be an isolated vertex. This kind of situation may also occur. that linked list itself is empty. Did you understand? When it will happen? When you are dealing with isolated vertex. When you will be dealing with isolated vertex. Very good, very good. Now this example, my dear students, was for an undirected graph, right? This was for an undirected graph. Now we all know we can have directed graphs also. We can also have directed graph. So I'll take a quick short example of a directed graph. 1, 2, 3, 4. I'll take only 4 vertices. Now these are the directions of my edges. These are the edges which are there. How many lists would be there? List will be 4. Number of vertices are 4. So number of lists will be 4. 1, 2, 3 and 4. These are my 4 linked lists. Now when I say this linked list, here this linked list are with respect to source vertex. Here this linked list are with respect to source vertex. Treat these linked lists as linked list for these respective source vertex. Now in linked list of 1, I will be storing only those edges in which 1 is acting as source in that edge. Very important. 1 is acting as source. Do you have any edge? Yes. This edge, that is 1, 2. In this edge 1, 2, 1 is source. Correct? So I will be storing 2 in my linked list of 1. Is it understood? Now, when I'm creating linked list for 2, I have to treat 2 as a source for those edges. In which edges 2 is acting as source? In edge 2, 3 and in edge 2, 4. Now here we should understand that for this particular edge, 2 is a destination, that is edge 1, 2, right? So this edge will not now contribute in the linked list of 2. I again repeat, the edge 1, 2 will not contribute in the linked list of 2 because in this 2 is a destination. While I represent this list, I am considering this particular vertex as the source vertex. So for which edges 2 is acting as the source vertex? Edge 2, 3 and edge 2, 4, right? So I'll be storing edge 2, 3. So I'll be storing 3 and for 2, 4, I'll be storing 4 in my linked list. Is it clear? Suppose I am having a loop also. I am constructing a loop. Suppose I am constructing a loop. Okay. So for 3, what will happen now? Only 3 will be there. Such kind of entry will also be there. Correct? And for 4 now, 4 is a source for 4, 3. Nothing else. This edge is 2, 4. So for 4 only one edge will be there, that is 4, 3. So this is the adjacency list representation of this particular graph. Is it clear? Any doubts in these examples? Yes, my dear students, any doubts?
No, sir.
Okay, so next we have to discuss one program for this graph implementation, but it is not possible to take it in 10 minutes. So I don't want to take it half. So in Friday's lecture, I'll teach you how to create now the program for this adjacency list. Okay, so I don't want to take it halfway. So we'll stop for today. Okay, we'll stop for today. Okay, on this you can write notes for this adjacency. What we have discussed today is graph representation. 2 types of representations are there. First is adjacency matrix. We have seen adjacency matrix for directed and undirected both. Similarly, we have adjacency list for undirected and directed both. Okay, tomorrow we'll discuss the graph implementation for the adjacency list. How we can actually write a program to store this information, this linked list, that we are going to discuss in tomorrow's lecture. Okay, we'll stop for today. Let me take the attendance first. Just hold on for a moment.